Bismillahirrahmanirrahim. Assalamu alaikum. My name is Surya Najaf and my roll number is 21TE06. Today I will be discussing lab number 4 of digital signal processing, and the title of the lab is Analyzing Discrete Time Linear Time Invariant Systems. The objective of the lab is to analyze discrete time linear time invariant systems. Response of an LTI system. Given impulse response of h of n and input n, the output y of n of an LTI system is given by the convolution sum, and the formula is given below. The MATLAB function for the convolution is conv h, x, and this function operates on infinite duration signals and assumes that the two sequences begin at n. Task A. How would you differentiate between a signal and a system? Explain key characteristics of each and provide examples to illustrate their roles in the context of signal processing. Signal. A signal represents a physical quantity that varies with time or space, conveying information. The key characteristics include amplitude, frequency, and phase. Examples include audio signals, images, sensor readings, and temperature measurements. In signal processing, signals are manipulated, analyzed, and processed to extract useful information or enhance specific properties. System. A system is a mechanism or process that operates on input signals to produce output signals. Systems can be physical devices, mathematical models, or algorithms. Key characteristics include linearity, time invariance, and causality. Examples include filters, amplifiers, communication channels, and control systems. In signal processing, systems are analyzed and designed to achieve desired signal transformations or responses. Task B. How does linear time invariant systems play a crucial role in digital signal processing? Considering their mathematical simplicity, adherence to superposition principles, and efficiency in frequency response analysis. Role of linear time invariant systems in digital signal processing. Linear time invariant systems are fundamental in DSP due to their mathematical simplicity, adherence to superposition principle, and efficiency in frequency response analysis. LTI systems enable straightforward analysis and design processes, allowing for efficient implementation of various signal processing techniques such as filtering, modulation, and signal reconstruction. The superposition principle states that the response of an LTI system to a sum of multiple input is equal to the sum of the individual responses to each input. Simplifying system analysis and facilitating modular system design. Additionally, LTI systems exhibit consistent behavior over time, enabling frequency response analysis techniques using like the Fourier transform. By exploiting the properties of LTI system, DSP algorithms can efficiently process signals in real time, making them indispensable in applications such as audio processing, image processing, telecommunications, and control systems. Task C. What are the common methods for signal decomposition, specifically focusing on techniques like impulse decomposition, step function analysis, even-or decomposition, and Fourier analysis? Explore how these methods contribute to breaking down signals and their applications in signal processing. So, Signal decomposition involves breaking down complex signals into simpler components to facilitate analysis and processing, and the common methods include impulse decomposition. Impulse decomposition is representing signals as a sum of scaled and shifted impulse functions, useful for analyzing system responses. Second one is step function analysis. In step function analysis, decomposing signals into step functions to study signal behavior under sudden changes. Third is even odd decomposition. In even odd composition, we separate signals into even and odd component based on their symmetry properties, aiding in signal analysis and synthesis. Fourth one is Fourier analysis. In Fourier analysis, we decompose signals into sinusoid components using the Fourier transform, enabling the frequency domain analysis and filtering. These methods contribute to signal processing by providing insights into signal characteristics, simplifying system analysis, and enabling efficient manipulation of signal components for various applications such as signal filtering, compression, and modulation. Task D. What is convolution and how does it play a significant role in digital signal processing systems? Explore the fundamental concept of convolution and elaborate on its importance in various DSP applications such as filtering, signal processing, and system analysis. Convolution is a fundamental operation in DSP used for filtering, signal processing, and system analysis. It involves combining two signals to produce a third signal that represents the mathematical integration of input signals, weighted and shifted versions. Convolution is crucial in DSP systems as it enables the following. The first one is filtering. Convolution is used to implement linear filters by convolving the input signal with the filter's impulse response. Number 2. Signal processing. Convolution allows for various signal processing operations such as smoothing, edge direction, and feature extraction. Number 3. System analysis. Convolution facilitates the analysis of linear time invariant systems by representing their input-output relationships through convolution integrals or discrete convolution sums. Convolution plays a significant role in DSP applications by providing a powerful mathematical tool for signal manipulation, system analysis, and algorithm implementation. Task E. When do we correlate two signals, and what are the key applications or scenarios where signal correlation is crucial in various fields such as communication systems, radar and sonar, image processing, biomedical signal processing, and control systems, wireless communications, and seismic signal processing? The signal correlation involves measuring the similarity between two signals over time or space. The key applications include: first one, communication system. Correlation is used for signal detection, synchronization, and error detection in communication system. Number 2 is radar and sonar. Correlation is essential for target detection, tracking, and discrimination in radar and sonar systems. Third one is image processing. Correlation is used for pattern recognition, template matching, and object tracking in image processing applications. Fourth is biomedical signal processing. Correlation aids in analyzing biomedical signals such as electrocardiograms, ECG, and electroencephalograms for diagnosis and monitoring. Number 5 is control systems. Correlation is used for system identification, adaptive control, and predictive maintenance in control systems. Sixth one is wireless communications. Correlation is utilized for channel estimation, equalization, and interference rejection in wireless communication systems. Number seventh is seismic signal processing. Correlation is employed for seismic delay data analysis, event detection, and subsurface imaging in geophysical exploration. Overall, signal correlation plays a crucial role in various fields by enabling signal analysis, detection, synchronization, and pattern recognition, facilitating advancement in communication, imaging control, and exploration technologies. Task number one. Make your own customized function that take two input signals from user and show convolution sum graphically. We made a function with the name myConv, which performs convolution between two discrete signals h and x and returns the results along with the corresponding index vector. X is the first input signal, nx is the index vector corresponding to x, h is the second input signal, and nh is the index vector corresponding to h. Here, signal 1 and signal 2 are defined as the arrays representing discrete signals. The convolution sum is defined with two input arguments, signal 1 and signal 2. The convol function is used to compute the convolution of the two signals, signal 1 and signal 2, and it is stored in the variable convolve result. We use the subplot subplot function. The subplot number 1 plots the signal 1 and uses the stem function. The stem plot is in blue color. The subplot 2 plots signal 2 using the stem function, and the subplot 3 plots the convolution result using the stem function. If we run this code, we see that the signal 1 is in blue, signal 2 is in red, and the third subplot is of convolution result of signal 1 and signal 2. So the third subplot, which is represented in green color, is the result of convolving signal 1 and signal 2, and the x-axis represents the sample number and the y-axis represents amplitude. Task number 2. Make your own customized function that take two input signals from user and use flip and slide method to show convolution sum step by step. We can use pause command to stay and see stepwise convolution results. Here, signal number 1 and signal 2 are defined as the arrays representing discrete signals. The function convolution step by step is defined with two input arguments, signal 1 and signal 2. Inside of this function, the lengths of the signal 1 and signal 2 are calculated by len1 and len2. The length of convolution results is computed using the formula convolution length, and it is done by adding length number 1 and length number 2 minus 1. An array convolution result is initialized with zeros, and it is used to store the result of the convolution. The second signal, signal 2, is flipped. The second signal here is flipped using the function flip lr to prepare it for the convolution. Convolution is then performed step by step using a loop from 1 to convolution length. Here. Now within each iteration, the range of overlap signal is determined. The overlap Elements are multiplied element-wise and summed up to compute the convolution result for the current step. The current convolution result is plotted using the stem function here, and there is a pause of 1 second to visualize each step. We can also adjust the pause duration as needed. And if it's not the last iteration, the plot is clear to prepare for the next step. After all these steps are completed, the final convolution result is plotted in a new figure. So when we run this code, here is the step-by-step convolution result. And once the step-by-step convolution was done, we obtained a final convolution result, where x-axis shows the sample numbers and y-axis shows amplitude. In task number 3, we have been given h of n and x of n when we have been asked to compute the response of the system. Here, x contains the input signals and h contains the values of the impulse response. N of x and n of h represents the indices of the input signal x and the impulse response h respectively. Furthermore, if we move to this line, we see that this line computes the convolution of the input signal x with the impulse response h using a custom convolution function myconvolve that we made here. It passes the input signal, its corresponding indices, the impulse response, and its corresponding indices to the myconvolve function. And the result of the convolution is stored in y, and the corresponding index vector is stored in n of y. For plotting, we use the stem function to create a stem plot with filled markers. And the x-axis represents the sample indices ny, and the y represents the amplitude of the convolution results. X label, Y label, and title are used to enable the axis and the title of the plot appropriately. So when we run this code, we get a convolution result of the signal X and H, where axis shows the samples and Y axis shows the amplitude. In task number 4, we have been given the impulse response of the system as n equals to this, for x of n equals to this, and we have been asked to find y of n. If we feed shifted version of the input signal, that is x of n, to the system, what kind of output signal will we receive? Here h is the given impulse response, x is the given input, and y and the convolution of the original input signal x with the impulse response h is computed using the conv function, which results in y. An index n of y is generated for y, and the convolution result of y is plotted against the index vector ny using the stem function to visualize the convolution result for the original signal. Here we define a shifted version of the input signal with the variable x shifted, and it shows two samples to the left using this circ shift function. The convolution of the shifted input signal x shifted with the impulse response h is computed using the convolution function, which results in the y shifted. And an index vector ny shifted is generated using y shifted to match the shifted input signal. If we plot this, we Here we observe a convolution result of y shifted where x-axis shows the samples of the shifted signal and y-axis shows the amplitude. Thank you. That's all from lab number 4.